How do you measure time? That's easy. You look at your phone, check the clock on the wall, or ask your smart speaker. Well, those are all pretty good answers for earthbound humans like us. But they become much more complicated when you start traveling through space. When it comes to clocks, there are two kinds. Those that keep track of time on Earth, and those that keep track of time in deep space. And as it turns out, those two methods don't always agree. In fact, they can be wildly different. On Earth, we use a clock that's based on the rotation of our planet. A day is divided into 24 hours, each hour into 60 minutes, and each minute into 60 seconds. But when it comes to human spaceflight, it gets a little more complicated. Because as we send astronauts farther, but even if you are just whizzing along in a high-speed spaceship at something like half the speed of light, time would pass only about 8 hours for you, while 14 hours pass on Earth. Multiply that by the amount of time you spend traveling, and you could end up having aged significantly less than your fellow Earthbound humans. And farther away from Earth, the effects of special and general relativity start to kick in. But fortunately, this is mostly theoretical. Right now, the fastest man-made object is the Parker Solar Probe, which reaches speeds of nearly 175,000 kilometers per second. But even that is only about 1% of the speed of light, so the effects of special relativity are negligible. It's not the most logical system ever, but it's useful for us humans since Earth rotates roughly once per day. That means time would pass more quickly on a spaceship that zoom in past Earth at half the speed of light than for someone who is hanging out on the surface of Earth. That might sound intimidating, but all it really means is that this clock uses superpositions and entanglement to keep better time than anything we've ever made before. But if it does, it could mean that everyone's personal clocks would be a lot more accurate. Now, again, these effects are only noticeable over extremely long periods of time. Remember those guys? They're still kicking, or we could base our measurement of time on the behavior of photons or other particles. We could carry these new clocks into space and leave some here on Earth. If you were to carry this clock with you into outer space, you could come back to Earth thousands of years later and find that time had stopped. Not because your clock broke, but because you left the frame of reference that defines our current measurements of time. But as long as there's movement in the universe, there will be time. If you enjoyed this episode, we'd love it if you took a second to show your support. It really helps us keep time and bring you awesome science content, so do not worry too much about your watch getting a little slow or your phone's battery dying. The universe will keep ticking even if we stop. And since they would all be measuring time based on the same constants of physics, they should all agree. Or at least they would if we could keep them accurate enough. According to NASA, an astronaut who spends just 1 year on the International Space Station will have aged only 70 milliseconds less than someone who stayed on Earth. We know that sounds dramatic, but hear us out. Our sun will run out of hydrogen fuel, and our current system of measuring time based on its rotation will collapse. But time itself won't stop. Even after the sun goes out, there'll still be radiation from distant stars and galaxies, and that means there'll still be the constant reminder of the passage of time. So how do we deal with that when we are sending people into space for months or even years at a time? This radiation is emitted by atoms of cesium-133, which is a radioactive form of the element. NASA says that a 1-year mission to Mars would result in the astronaut aging 11 minutes less than someone who stayed on Earth. All this means that any human missions to other planets will require careful planning, so that astronauts and mission control can stay on the same page. A 2-year mission to Mars and back could result in the astronaut aging 37 minutes less. Cesium atoms in a vacuum will emit this radiation every 9,192,631,770ths of a second, and that's what a true second is based on. This is known as Coordinated Universal Time, or UTC, and it's what scientists use around the world to keep time. Well, let's take it from the top. There are basically 2 ways to define a second. So when NASA sends spacecraft into deep space, they have to carry atomic clocks that use things like vibrating quartz crystals to keep time. These clocks aren't perfect, but they're accurate enough that NASA can assume that 1 second on Earth is pretty close to 1 second in space. But it's just an approximation. A true second is defined as the duration of 9,192,631,770 periods of radiation. The trouble is, this kind of clock does not work well in space, because nothing out there is rotating once per day or emitting cesium radiation. That way, when signals are sent back and forth between Earth and a probe on a long voyage, scientists can assume both parties are measuring the duration of the trip in the same way. Special relativity says that time passes slower for objects that are moving relative to one another. This effect becomes more pronounced the faster you go. And if that seems like a huge problem, well, it sort of is. However, general relativity says that time passes slower for objects that are closer to massive bodies, like planets and stars. So, as a person travels farther and farther away from Earth, they will age slower than their friends back home. But what happens when we start sending people on longer journeys, say to Mars or beyond? Well, the difference in age becomes more significant. And if we want to make things really complicated, we can also factor in the effects of cosmic radiation on an astronaut's body clock. But before we get too worried about the complicated mathematics of keeping time, we need to talk about a whole other complication that might put a wrench in our space plans. In July of 2020, researchers reported that they had created a new clock that's powered by quantum mechanics. It is not yet clear whether this technology will ever end up in your house or on your wrists, and a lot more accurate means that one day we may no longer need to measure time in seconds or minutes or hours. Time, as we know it, could end. If we had a bunch of incredibly accurate quantum clocks, we could define time in terms of things that are constant, like the frequency of radiation emitted by cesium-133 atoms, and that would mean that time would no longer be dependent on the rotation of our planet. Theoretically, we could make a clock so accurate that it would never have to be adjusted. Think about it. Eventually, the Earth will die. We may one day measure that time in units that we haven't even defined yet. And speaking of keeping time, thanks for sticking with us until the end of this video. Why does time matter? What's so important about it? And why do we go to such lengths to keep track of it? Hi, I'm here with Minute Earth. It tells us when to wake up, when to eat, when to work, when to play, and even when to sleep. It helps us to measure, organize, and control our experiences. Consider measuring. When you say, "I'll be there in 10 minutes," you need some way to keep track of those 10 minutes. Or when you set an oven timer for 20 minutes, you need to know that your counting system works, and that you can rely on it to be accurate. It's considered to be the earliest known instrument for measuring time. Back then, people used the position of the sun in the sky to estimate the time of day, and sundials like these were used throughout ancient Egypt, Greece, and Rome. If not, your dinner might burn, or you might be late to an important meeting. Other cultures developed other techniques. For example, the Mayans used a carefully calibrated water clock, and the Chinese used a weighted hourglass. The winning solution, John Harrison's marine chronometer, relied on a new device called a balance spring, which oscillated at a constant rate regardless of changes in temperature or altitude. These springs allowed for incredibly precise timekeeping. Harrison's chronometers lost less than a minute per year. In the 1400s, the inability to keep accurate time while at sea was actually a major obstacle to finding a faster route to Asia. It helped establish colonies and trade routes on every continent and fueled the age of exploration. In the early 1900s, telegraphs and telephones became widespread. UTC is currently maintained by a network of over 400 atomic clocks, operated by national metrology institutes and coordinated by the International Telecommunications Union. Atomic clocks use the vibrations of atoms to count time with incredible precision. They are the most accurate timekeeping devices ever created. Radio broadcasters took over as the primary source of time information, and as computers and smart devices became ubiquitous, getting the right time became essential for coordinating transactions, launching satellites, and ensuring the smooth operation of global networks. And musicians and by viewers like you who helped bring this episode to the whole wide world. And we've got a lot more time-related videos where this came from. You can learn what Einstein meant when he said that time is an illusion, or find out whether time travel is possible. You can also binge classic episodes, like how does the internet work, or what really happens to your body after you die. Despite the amazing technologies we've developed to measure time, organize our lives and coordinate with others, we still struggle to manage our own pace. We experience time differently, depending on our age, background, personality, and circumstances. Some of us are impatient, while others feel like time is slipping away. Some of us find time quickly when we're having fun, while others wish the moments would slow down. It also led to the standardization of time. Before the mid-1800s, time varied from place to place. When the sun reached its highest point in the sky at noon in London, it was only 11:39 a.m. in Los Angeles. Sometimes we have to round off the time to account for leap seconds, which are added to keep coordinated universal time aligned with the Earth's rotation. But beyond that, there's no discrepancy between the actual time and the time on your phone. Philosophers pondered the nature of time, and theologians debated its role in salvation. Scientists sought to understand its true nature, and inventors devised ingenious ways to measure it. But maybe the real answer lies in how we experience time, which is always passing, always moving forward, always slipping through our fingers. And maybe that's why time matters so much to us. It reminds us that life is fleeting, and that we should make the most of every moment. People kept different times based on their location, and there was no official way to convert between them. The problem was so serious that the Portuguese even offered a noble title, 100,000 gold crowns, to anyone who could solve it. They decided to adopt a single standardized time for the entire planet, which divided the world into 24 time zones, each separated by 15 degrees of longitude. For example, California was 8 to 7, just like New York was 4 to 3. But as transportation improved and people began to travel more frequently between cities, the half-hour differences caused increasing inconvenience. And so, over time, many locations shifted their time zone to a more convenient whole number value. Some moved forward half an hour to make it easier to align with the business hours of other regions. Other places moved backward to take advantage of daylight hours. Today, there are only 5 time zones in which most places observe half-hour offsets from standard time, namely Hawaii, Newfoundland, Greenland, Samoa, and Nepal. They also designated a starting point for these longitudes, the Royal Observatory in Greenwich, England, and so the world began to operate on Greenwich Mean Time, or GMT, but none of these methods could tell you precisely what time it was, nor could they tell you what time it was in another part of the world. And that was a problem. But in truth, None of this would be possible if our species hadn't first solved a much more fundamental question, which was how to tell one moment from the next. Our days are packed with obligations, errands, appointments, and activities. There was just one problem. It never worked properly. Pendulum clocks were far more accurate than previous timekeeping devices, but they too had their limitations. They were sensitive to temperature changes and humidity, so their accuracy varied with the seasons. They also couldn't easily be transported because the pendulum had to hang freely to work, so they weren't particularly useful for coordinating across large stretches of space. Then there was the German mathematician and astronomer Peter Henlein, who, in 1510, constructed a portable clock with a spring-driven mechanism. He essentially invented the pocket watch, though his devices were large, inaccurate, and unreliable. Knowing what time it is allows us to make choices about how we spend our time. That is, we can try to, at least in general. Humans don't like feeling rushed or stressed, but sometimes we have no choice. If you've ever been in a hurry to catch a plane, you know what I mean. But knowing what time it is gives us the chance to avoid those situations, if we can help it. With a little bit of planning and forethought, we can try to stop ourselves from being late. If we didn't have some way to organize all that information, we couldn't function. A schedule gives us a sense of order and predictability. It helps us get things done. And if we had no concept of time, we wouldn't be able to coordinate with anyone else to do anything. Timekeeping allows us to plan ahead and prepare. We can anticipate sunrise and plant our crops accordingly. We can set reminders and follow through on tasks. So let's take a minute and talk about why time matters. Timekeeping is a technology that has shaped the way we live. We humans have always needed to know what time it was for a variety of reasons, says historian and science educator Richard Serotops. And then there's organizing. But perhaps most importantly, timekeeping helps us control our experiences. And that desire for control may explain why we humans have gone to such great lengths to understand and predict time. This sundial dates back to around 3,500 years ago. Of course, there were problems with this method, namely that it only worked outside during the day and it wasn't very accurate. As trade routes expanded and sea travel increased, merchants and sailors needed a way to coordinate across vast distances of land and sea. This quest to understand time motivated some of the greatest scientific minds of the 15th century, including Leonardo da Vinci, who designed a device called a paratar, a complex mechanical clockwork contraption intended to measure both time and latitude. It wasn't until Christian Huygens, a Dutch scientist, built a precision pendulum clock in the mid-1600s that humanity really started to get a handle on time. And that problem still had been solved by the early 1700s, when the British Royal Society offered a prize for the best device to measure longitude at sea. The ability to accurately measure time on a global scale gave us the confidence to undertake epic journeys across the oceans. Then, in 1884, representatives from 26 countries met at the International Meridian Conference in Washington, D.C. to discuss the matter. At first, the time zones stuck primarily to whole number values. As the world became increasingly interconnected, the need for precise and consistent timekeeping only grew. So in 1967, the Coordinated Universal Time Scale, or was established as the world's official time standard. In fact, they are so accurate that there's really no such thing as a wrong time anymore, and yet some of us still find ourselves running late. As long as humans have been keeping track of time, we've also been trying to understand it. Thanks for watching this episode of Minute Earth. Minute Earth is made possible by a team of talented writers, editors, scientists, artists, Even before mechanical clocks were invented about 500 years ago, people still had ways of measuring time in various ingenious ways. In this video, we're going to explore some prehistoric and ancient methods of telling the time. So let's get to it. People would keep track of the position of the sun throughout the day and its corresponding change in altitude through the seasons. Since the sun is about 400 times larger than the moon and moves faster across the sky, it's a much more reliable marker for tracking time than the moon. Astronomers have found that the three pyramids of Giza are aligned almost perfectly with the three stars in Orion's belt. They were built around 2560 BC, but the phenomena linking them to Orion was first noticed by researchers in the 1980s. The Maya civilization thrived in what is now Mexico, Guatemala, and Belize. Between 2000 BC and 1697 AD, they created intricate calendars based on astronomical observations and used them to plan agricultural activities and religious ceremonies. From observing solar rhythms and aligning structures with celestial bodies, to developing sophisticated calendars and using the menstrual cycle to measure time, ancient civilizations developed ingenious methods to keep track of time. Each culture's approach reflects their deep understanding of astronomy, mathematics, and the natural world. The Incas' road-based timekeeping system stands out as a remarkable achievement, allowing them to synchronize their vast empire through the relay of fire signals. As we continue to explore the mysteries of our past, we can marvel at the incredible ways that early humans kept time and understood the world around them. One of the most impressive achievements of Maya timekeeping was their development of a highly accurate 260-day ritual calendar known as the If you have a suggestion for a future video, let us know in the comments below. Thank you for watching. This calendar consisted of 20 named days, each associated with a particular deity. Every day had both a day sign and a number, creating a unique combination for each day of the year. The Maya also kept track of time using a 365-day solar calendar known as the Hob, which closely resembled the Gregorian calendar used today. This calendar consisted of 18 months, each month containing 20 days with a 5-day period at the end of the year. The Maya also devised a complex system of vigesimal mathematics, using the base 20 rather than the base 10 used in most modern systems. This allowed them to create calendars with precise astronomical alignments, such as the Maya calendar predicting the return of Comet Halley in 1531 AD, nearly 300 years before it actually occurred. The Maya's advanced understanding of astronomy and mathematics enabled them to develop sophisticated calendars and predict astronomical events with remarkable accuracy. Their ability to keep time played a crucial role in their society, helping them to plan agricultural activities and religious ceremonies with precision. Robert Balvac, author of Orion and the Pyramids, believes that Egyptians used the constellation as a guide to help them locate the true east and true north when building the pyramids. The Inca Empire flourished in South America between the 13th and 16th centuries. Adian was known for its impressive road system, which stretched over 40,000 kilometers. The Inca used their roads not only for communication and trade, but also to synchronize time throughout their vast empire. At the center of the Inca road system was the Capac Own, which connected the empire's capital Cusco to its farthest reaches. Along this main road, there were watchtowers at regular intervals, where fires were lit to signal important events, such as sunrise and sunset. Runners would then relay the message from tower to tower, ensuring that people throughout the empire knew the time without relying on clocks or other artificial devices. This method of timekeeping was crucial for the Inca, who relied on the sun for agricultural planning and religious ceremonies. By using the natural phenomena and their road system, the Inca were able to keep their entire empire synchronized. But some experts disagree. believing that any connection between the pyramids and the stars is purely coincidental. Regardless, it's undeniable that the Egyptians possessed extensive astronomical knowledge and used it to develop sophisticated calendars. Egyptian calendars consisted of 365 days, divided into 12 months, each month containing 30 days plus 5 days added at the end of the year. Interestingly, the Egyptians kept accurate records of the annual flooding of the Nile River, which coincided with the heliacal rising of Sirius, the brightest star in the sky. Farmers used this event to predict the beginning of the Nile's flood season and adjust their planting schedule accordingly. The most primitive form of a sundial was probably the simple observation of the sun's position at midday. When it reached its highest point in the sky, researchers believe that ancient Egyptians observed the cyclical nature of women's Earth and developed a calendar based on this phenomenon. This discovery was made by analyzing ancient Egyptian texts, including a papyrus dating back to 1800 BC that depicts a woman standing next to a pool with her arms raised, signifying her period. This image suggests that Egyptians considered menstruation a significant part of the female experience and developed a system to track it. Another piece of evidence is a stele inscribed with a lunar calendar showing the phases of the moon, alongside symbols thought to represent menstrual blood. The length of a woman's cycle averages around 28 days, which aligns with the number of days in the phases of the moon. Therefore, the Egyptians may have initially used the lunar calendar to keep track of time, then switched to a solar calendar after realizing the limitations of the lunar calendar. The Egyptians' keen observation of both natural phenomena and human experiences showcases their advanced understanding of science and daily life. This method is so intuitive that it is believed to have been used all over the world independently by different cultures. During prehistoric times, humans tracked shadows cast by objects like trees or stones to estimate the passage of time. A large upright stone monolith with a smaller rock placed nearby would cast a shadow that would shrink and grow throughout the day. To improve the accuracy of their timekeeping, our ancestors also learned to read the positions of stars in the sky, particularly the movements of those close to the celestial equator, where the Earth's path of rotation intersects the celestial sphere. As the Earth rotates, these stars appear to rise and set, offering a cyclical rhythm that can be used to keep time. Using star clocks was especially helpful during the night and in cloudy weather when the sun was not visible. This knowledge of astronomy helped our ancestors predict solstices and equinoxes and perform agricultural activities at the right time of the year. The earliest form of keeping time was by observing solar rhythms. Located in Wiltshire, England, Stonehenge is a remarkable structure built around 3000 BC, consisting of a circular arrangement of standing stones. It is believed that Stonehenge was constructed in 3 phases between 3100 BC and 1500 BC, with each phase taking approximately 500 years to complete. Archaeologists believe that people came from miles away to this site in prehistoric Britain specifically to observe the summer solstice. Why? Well, because one of the stones, known as the heel stone, is perfectly aligned with the rising sun during the summer solstice. At this time of year, the sun rises directly between 2 of the standing stones called the twin stones. According to archaeologist Timothy Duff, the rising sun would have been visible between the twin stones only for a few minutes before it began its arc behind the other stones. There are several other fascinating alignments at Stonehenge. For example, there is an avenue of 100 trees pointing towards the midsummer sunrise and the winter sunset. There is also a pair of ditches and banks, forming a gigantic pair of compasses pointing towards the solstice. And if you walk around the monument in an anti-clockwise direction, the entrances to the outer and inner circles are perfectly aligned with the midsummer and midwinter solstice. These alignments suggest that Stonehenge was used as a place for religious ceremonies and rituals connected to the cycles of the sun and the changing seasons. Moving on, let's look at one of the most famous prehistoric examples of keeping time, which is Stonehenge, another well-known archaeological site that shows evidence of timekeeping is the pyramids of Egypt. And speaking of ancient Egypt, they also kept time by measuring the length of a woman's menstrual cycle. You heard that right. Moving on, let's explore another ancient civilization that developed sophisticated methods for keeping time, the Maya. And finally, let's look at another remarkable ancient civilization known for its timekeeping abilities, the Inca. In conclusion, our exploration of ancient timekeeping methods reveals the ingenuity and curiosity of early humans. If you enjoyed this video, please leave us a like and subscribe for more content. If clocks and watches are your thing, then this episode is absolutely for you. Join us as we explore some of the oldest surviving examples of human ingenuity and the many clever methods our ancestors used to keep track of the time long before the invention of the digital clock or the wristwatch. At number 2, we have the sundials and water clocks from ancient Babylon, Egypt, and Greece. This device that we're going to be looking at first here has survived since the time of the Babylonians. It is currently being held by the British Museum and is thought to be one of the earliest examples of astronomical instruments to have survived since antiquity. The water level in the receiving container would rise up, and when it reached the maximum level, it would trigger a small boat to sail off the end of the pool. While the Egyptians used the water clock as a simple out-of-bounds tool, the Greeks took it a step further and invented the first mechanical water clock. A vessel full of water is raised to the top of a high column by means of a pump, and then flows through a small aperture in the vessel and is received in a basin. Discovered in 1901 at the ancient Egyptian site of Thebes, it's commonly referred to as the Thebes water clock. According to the first theory, it was a simple overflow device, like we saw earlier. That means that the water would pass through the spout in the front of the device and empty into the base. And you can go see it for yourself if you'd like to try and solve the mystery. Once the jar was empty, it would float up and turn the figure of Ra around. This one was discovered in 1938 at the Han Dynasty tomb of Lechang, who was a prince of the kingdom of Changsha. This is because the entire device was carved out of a single piece of jade. Those are just a few of the many incredible inventions that humans have come up with over the years to tell the time. From sundials to water clocks to rooster clocks, there is no shortage of creative ways to keep track of the hours. Which one of these devices was your favorite? Let us know in the comments below. And don't forget to subscribe if you haven't already. See you next time. Well, that's because the position of the rooster is symbolic of a chicken pecking at grain. Specifically, it represents a moment in time when roosters were typically crowing. Basically, this clock uses the position of the rooster in relation to the sunrise and sunset to tell the time. Because chickens are known to crow when the sun rises, they used that as a starting point for their clock. At the top of the jade carving is a rooster, which is perched on a ball. Below the rooster is a set of 4 dials that indicate the month, the day, the hour, and the minutes. These dials are all connected to a central gear in the center of the device. As the minute's hand moves around the dial, it turns a small wheel, which in turn rotates the hour hand. And the month and day hands move around their dials once every 24 hours. The tomb dates back to around 113 BC, so the artifact is nearly 2,000 years old, and it's currently housed in the Yunnan Provincial Museum in China. However, there is no record of such a device in any ancient texts. The other theory is that it was a much more advanced inflow device that would have required the water to be pumped upwards. This would have been a far more complicated device and would have been closer to the type of water clock that was used in Greece. Currently, It's housed in the Ashmolean Museum in Oxford, England. It dates back to around 1350 BC, and it is considered to be the world's oldest surviving example of a water clock. There is a pipe extending through the column and connected with a bladder. As the water descends, air is forced into the pipe and the bladder expands and floats. Each year, the river would flood and cover the land in silt, which was incredibly fertile and allowed the Egyptians to grow 2 crops per year. Therefore, predicting when the floods would happen was of paramount importance. It was originally suggested that the ark could have been placed at the entrance to the Temple of Min, the god of fertility, and that each day it would have indicated the progress of the annual floods. But research suggests that it may have instead been used in conjunction with other tools to help predict the floods. We simply don't have enough evidence to say for sure. When the bladder reaches a certain point, a weight causes it to descend and lets in water until the bladder is filled. Then the process reverses. Hero went on to explain that by adjusting the size of the aperture in the vessel, you could increase or decrease the rate of flow and therefore the accuracy of the clock. He also came up with several different ways to display the time, including using floating balls, dials and pointers. These devices were called clepsydra, the same name given to the Egyptian outflow device, but they worked in a completely different manner. Instead of letting gravity pull the water down, they pumped the water up using a series of pistons and rods. By controlling the amount of water being pumped, they could control the amount of water flowing out of the device. The inflow water clock was, therefore, far more accurate than the outflow type. This boat contained a small statue of the god Ra, who was the personification of the sun. When his boat sailed away, it signaled that the day was finished. These types of water clocks were extremely popular during the New Kingdom of Egypt, and you can see an image of one in the tomb of Queen Nefertari, who was the great king's favorite wife, one of the most famous examples of a Cleopatra. However, can be found in the great temple complex of Here the rising water level was used to open and close the great doors that sealed off the Holy of Holies, the innermost chamber of the temple. It was most likely made around 1800 BC in Babylonia. It dates back to a time when the Babylonians were known to have developed astronomy into a science, and it continued to be used until the Islamic Golden Age, more than 1,000 years later. The device itself was designed to sit vertically with its triangular base pointing north. Its gnomon or pointer would cast a shadow on the 7 horizontal plates and thus show the hours of the day. The interesting part about this sundial is that it has been engraved with the zodiac signs along with their respective hour divisions. For example, the sign of Aries is found at the 1st hour and Taurus is found at the 2nd. What makes this sundial really interesting, though, is that it has the oldest known copy of the mul, a pin, which is a Babylonian star catalogue that dates back to the time of the Kassite dynasty in the Second Babylonian Empire. This is also the world's oldest known trigonometry table. So not only did they use this to tell the time of day, but they also used it to identify constellations in the sky and learn about their positions, something which was very important to them religiously. For the next device, we travel to ancient Egypt, where we find another form of the water clock, known as the. This one dates back to around 1500 BC, and was discovered in the tomb of an ancient Egyptian official named Omen, who was the treasurer of the royal household under the 14th pharaoh of Egypt's 18th dynasty. In ancient Egypt, water clocks were a popular way of measuring time, especially in courts and in temples, and were generally preferred over sundials because, unlike sundials, they could operate at night and indoors. They were also much more precise than sundials, because the flow of water is far more consistent than the movement of the sun across the sky. This particular water clock consisted of a central container filled with water that would slowly overflow into another container. Traveling west now, we come to the next example of early water clocks, which come to us from Greece. But these ones take things a step further. One of the most famous Greek clepsydras was created by Hero of Alexandria in the 1st century AD. He described it as follows. While there isn't any physical evidence of Hero's water clock, there is a replica of it that was constructed in the 1970s and is currently on display at the Istanbul Archaeology Museums. Moving on, we'll talk about one of the most mysterious timekeeping devices ever discovered. First, let's look at the device itself. What makes it so mysterious is that we do not know exactly how it works or what it was actually used for. There are two main theories about how it functions. Some scholars believe that this device wasn't just a simple clock, but was instead used to predict the flooding of the Nile River. As we said earlier, it's currently housed in the Ashmolean Museum in Oxford, England. For our final artifact, we head east to China, where we find yet another unique timekeeping device. It's called the chicken foot clock. And as its name suggests, it looks like a chicken's foot. But why is it called a chicken foot clock? So there you have it. There's a certain feeling that comes with solving a difficult problem. That moment when you understand how something works or how to fix it, it can be exhilarating. So imagine if you were the first person to experience this feeling for a particular problem. How much more rewarding that must feel. Welcome to my channel. Today we'll be looking at 4 mechanical engineering problems that were solved for the very first time in antiquity. According to legend, the first self-propelled automaton was created by Yushainan in 400 BC, a philosopher and a scientist. This device was invented around the 3rd century BC, and it was used to move water from a low-lying area to a higher elevation. It consists of a spiral-shaped pipe with a handle that is attached to a central shaft. It was created in 1094 AD during the Song Dynasty in China, and it stands as a testament to the incredible engineering and technological capabilities of the ancient Chinese. You can also watch other videos like this one on the screen. Thanks for watching. The main purpose of this tower was to accurately tell the time as well as to indicate the sunrise and sunset. It was equipped with a number of sophisticated devices, including a water-powered astronomical clock, a sundial, and a system of bells and drums that were used to signal the time. The astronomical clock was powered by a series of connected water wheels that were driven by water flowing from the top of the tower. The clock had a vertical axis and featured a series of rotating discs that were used to keep track of the hours, minutes, and seconds. This was an incredibly complex mechanism for the time period, and is considered to be one of the earliest examples of a mechanical clock in the world. The sundial was located on the top of the tower and was used to indicate the time during the day. It consisted of a gnomon, a vertical pointer-like structure that cast a shadow on a circular dial, marked with the hours. As the sun moved across the sky, the shadow from the gnomon would move around the dial, indicating the time. The system of bells and drums that were used to signal the time was activated by the astronomical clock. Every hour, the clock would strike a bell, and every 15 minutes, a drum would be struck. This allowed people in the city to keep track of the time, even from a distance. The tower itself was an impressive feat of engineering. It was 120 feet tall and was made of brick and wood. It also featured a number of other astronomical instruments, including an armillary sphere and a lunar calendar. The entire structure was designed to be both functional and aesthetically pleasing. It was meant to serve as a reminder of the Song Dynasty's commitment to scholarship and the pursuit of knowledge. Unfortunately, little remains of Susong's clock tower today. It was destroyed in a series of earthquakes that struck the city of Kafung in the 13th century. However, there are a number of detailed descriptions of the tower that were written during the Song Dynasty. These descriptions, along with archaeological evidence, have allowed historians and engineers to get a good understanding of how the tower worked and the level of sophistication that the ancient Chinese had achieved The engineering and technology displayed in Susong's clock tower is truly remarkable. It's a testament to the ingenuity and creativity of the ancient Chinese, and a reminder of the importance of preserving our cultural heritage. As the handle is turned, a screw rotates, which moves water up the pipe. Although simple in concept, the Archimedes screw was a revolutionary invention. It allowed farmers to irrigate their fields more efficiently, which led to increased food production. It also made it possible to remove water from mines, which allowed miners to work in safer conditions. In addition, the Archimedes screw was used to drain swamps and to build dams. It even saw military application, being used to move water from besieged cities to the attacking armies. The genius of the Archimedes screw lay in its simplicity. It was a relatively inexpensive device to construct, and it required minimal maintenance. It also didn't require a large workforce to operate it. This made it an attractive option for a wide range of applications. For example, a single person could easily operate the machine to water a field, making irrigation much easier than other methods that were available at the time. In fact, the Archimedes screw is still being used today in some parts of the world to move water from one place to another. It's a testament to the genius of Archimedes that his invention has stood the test of time. He wanted to create a machine that would automatically pour wine without the need for a servant. This is because accurate timekeeping is essential for many applications, from navigation to telecommunications. However, the quest for ever more precise clocks has led to some strange and unusual designs. One such example is the Foucault pendulum, which was invented by French physicist Foucault in 1851. This pendulum is used to demonstrate the rotation of the Earth. It consists of a long metal rod that is suspended from the ceiling of a building and a heavy weight that is attached to the bottom of the rod. When the pendulum is released, it swings back and forth in an arc. As the Earth rotates, the pendulum appears to change its path and eventually returns to its starting point after making a complete circle. This is because the Earth has rotated beneath the pendulum during its swing. The Foucault pendulum is an impressive feat of engineering, and it is a reminder of the ingenuity of early engineers. By understanding the principles behind the Foucault pendulum, engineers have been able to develop more accurate clocks and timekeeping devices. His invention consisted of a water clock that controlled a set of gears, which would then move a series of levers that would control the pouring of the wine. While there is no physical evidence left of Yoshino's original invention, later versions were built and have survived. One such example is the device known as the Drunken Immortal. This device was created in the Temps dynasty, and it uses water to power a series of gears, which then rotate the arms of a seated figure. As the arms rotate, they pour liquid from a series of small containers which are attached to the elbows. The Drunken Immortal demonstrates many of the key elements of classical automata. These include the use of water as a power source, the use of gears to transfer motion, and the use of levers to create movement in a desired direction. The inclusion of these elements is what makes this piece of engineering so impressive. To put this in perspective, these types of machines are similar to modern-day robots. We may not think of ancient China as having had the same technological capabilities as modern-day China. But without advances such as these, we wouldn't be where we are today. If you enjoy this video, be sure to subscribe and hit the like button. But the truth is that early engineers developed some pretty complex machines. One of the most famous examples of an automated machine is the Antikythera mechanism. This device, which was found in an ancient shipwreck off the coast of Greece, is thought to have been used to predict astronomical positions and eclipse. It was created around the 2nd century BC and is considered to be one of the most sophisticated pieces of engineering ever discovered from the ancient world. The complexity of its design far surpasses any other device found in the region during that time period. And if you want to watch more videos like this, then you should definitely check out our other videos as well. The idea of automation has been around for centuries, though we rarely think of the ancient world as particularly innovative. However, the Greeks weren't the only ones creating advanced machines. In fact, the earliest known automata was created in China over a century earlier. One of the most famous examples of mechanical ingenuity in antiquity is Archimedes' invention of the Archimedes screw. Over the last few decades, engineers have become increasingly interested in developing new ways to measure time. Another impressive feat of mechanical engineering is Su Song's Tower of the Sun, also known as Su Song's Clock Tower. If you enjoyed this video, please leave a like and subscribe to the channel. There are over 2 billion Muslims in the world today, making it the second largest religion by population behind Christianity. But what many people don't know is that during their peak, Islamic civilization was one of the most advanced in the world. The astrolabe was an essential tool for sailors and travelers, allowing them to determine their location and the time of day using the positions of the stars. Well, in this video we'll explore the complex inner workings of a traditional astrolabe and shed light on the brilliant minds behind its invention and join us as we delve into the fascinating history of one of the most remarkable achievements of Islamic horology. Some astrolabes also functioned as sundials or water clocks, demonstrating the versatility and ingenuity of Islamic horologists. Together, we'll uncover the secrets of these magnificent devices and pay tribute to the brilliant minds that brought them to life. Their creations not only served practical purposes, but also exemplified the aesthetic sensibilities of the time, often adorned with beautiful designs and calligraphy. Unfortunately, many of these masterpieces were lost to history. Victims of conflict and changing tides, they developed innovative teaching methods, established influential schools of thought, and translated ancient texts, preserving and advancing human knowledge. He is best known for his remarkable contributions to the field of mechanics, and his innovative creations left a lasting impact on Islamic horology, the study of timekeeping devices. From an early age, he displayed a keen interest in science and engineering, particularly in the design and construction of mechanical devices. He received a comprehensive education in various subjects, including mathematics, astronomy and mechanics, laying the foundation for his future inventions. While some consider it to have begun with the establishment of the Abbasid Caliphate in 750 CE, others argue for a later start. His inventions and writings earned him recognition and admiration throughout the Muslim world. Its origins can be traced back to ancient Greece, but it reached its peak of sophistication during the Islamic Golden Age. Created in 1206, this monumental work of engineering showcased his mastery of mechanics and his deep understanding of astronomy. A rotating arm known as the alidad allows for adjustments and measurements. The reti, a network of engraved lines and pointers, interacts with the mater to display various celestial phenomena. During the Islamic Golden Age, Muslim astronomers and mathematicians contributed significantly to our understanding of the cosmos, which in turn enhanced the utility and accuracy of the astrolabe. Additionally, there might be rings or tables on the astrolabe that provide further information based on the user's location and the time of observation. It incorporates advanced mathematical calculations and astronomical tables, reflecting the deep knowledge and expertise of its maker. The inclusion of differential wheels and other sophisticated mechanisms enabled the astrolabe to display various celestial phenomena with precision. It embodies the spirit of curiosity, exploration, and innovation that characterized this era, reminding us of the profound contributions of Muslim scholars to the advancement of science and technology. If you want to continue exploring the rich history and culture of this era, I recommend checking out additional resources. you can delve deeper into the fascinating world of Islamic art, architecture, and scientific achievements. His inventive spirit and dedication to the advancement of knowledge continue to inspire awe and admiration. Its ornate design and craftsmanship demonstrate the aesthetic, sensibility, and cultural richness of the Islamic Golden Age. Your support will help us continue producing quality videos on underrepresented historical topics. Thank you for watching, and I encourage you to keep learning about the amazing achievements of Muslim civilizations. Until next time, stay curious and keep exploring the wonders of our shared human heritage. The fusion of science, mathematics, and art is a testament to the intellectual achievements of Muslim scholars and engineers. By aligning the astrolabe with the horizon and the celestial poles, one could use the position of stars or planets to determine latitude, longitude, and the time. For example, by sighting the altitude of Polaris, the North Star, the observer could calculate their latitude. Created by the renowned astronomer and engineer Al-Samarkandi in 1221, this astrolabe is a masterpiece of Islamic horology. Crafted with a brass disc as the mater, it features intricate engravings and inscriptions, showcasing the artistry and attention to detail of its creator. The reti is beautifully decorated with geometric patterns and the signs of the zodiac, adding an aesthetic dimension to its functionality. The astrolabe's ability to provide accurate astronomical data made it an invaluable tool for sailors, astronomers, and travelers during the Age of Discovery. Sadly, the great engineer passed away in 1206, leaving behind a legacy that has stood the test of time. His inventions and writings continue to be studied and appreciated, and his name remains synonymous with ingenuity and innovation in the history of science. The elephant clock featured a complex system of gears and differential wheels that enabled it to keep accurate time and display the positions of the moon and planets. Its intricate design and astronomical capabilities made it a marvel of its time. One of his most notable works was the Kitab al-Fi al-Hiyat al-Jabari, also known as the Book of Knowledge of Ingenious Devices. This comprehensive treatise presented a wide range of mechanical inventions, including automata, water clocks, astronomical instruments, and musical devices. Similarly, the end of the Golden Age is often placed at the decline of the Ottoman Empire in the 17th century. Nevertheless, the Islamic Golden Age remains a pivotal period in Muslim history, celebrated for its intellectual, economic, and cultural achievements. Furthermore, trade flourished along established land and sea routes, connecting diverse cultures and facilitating the exchange of ideas and goods. This economic prosperity fueled urban growth, artistic innovation, and the patronage of science and learning. However, a few examples have survived, offering us a glimpse into the extraordinary achievements of Islamic horology during the Golden Age. The Islamic world's passion for astronomy and precision. Engineering led to the creation of some of the most intricate and beautiful astrolabes ever made during what is referred to as the Islamic Golden Age, roughly spanning from the 8th to the 14th century. Muslim scholars made groundbreaking discoveries and inventions in various fields, including science, mathematics, astronomy, medicine, and art. It marked a golden age of intellectual and artistic achievement, leaving an indelible mark on various fields of knowledge. One of the most notable contributions of Islamic horology is the development of a sophisticated astronomical instrument used for navigation and timekeeping. But have you ever wondered how complicated these horological instruments actually were? During the Islamic Golden Age, horologists in Muslim lands pushed the boundaries of mechanical ingenuity, creating elaborate astronomical instruments like the astrolabe. These devices allowed users to track celestial bodies and calculate time with astonishing accuracy. What's more, they often incorporated intricate gearwork, showcasing the advanced engineering skills of the era. One of the most famous examples is the elephant clock created by the polymath Al-Jazari around 1206. This monumental work of engineering featured a complex system of gears and differential wheels that allowed it to keep accurate time and display the positions of the moon and planets. In fact, the sophistication of these devices often extended beyond mere timekeeping, incorporating features such as automatic winding and even music. If you're recaptivated by these technological wonders and eager to learn more about the intricate mechanisms behind them, then I invite you to stay tuned for an exciting journey through the world of Islamic horology. The Islamic Golden Age refers to a period of cultural, economic, and scientific flourishing in Muslim history that occurred between the 8th and 14th centuries. During this era, Muslim scholars and thinkers made significant contributions to mathematics, astronomy, medicine, philosophy, and more. However, it is important to note that the dates and characteristics of the Islamic Golden Age can vary depending on the region and different interpretations. Al-Jazari was a brilliant Muslim engineer and inventor who lived during the Islamic Golden Age, a period of cultural and scientific flourishing in Muslim history. Al-Jazari was born in 1136 CE in the city of Jazira, located in what is now modern-day Iraq. Throughout his career, Al-Jazari held esteemed positions in various courts, including the service of the Caliph of Baghdad and the ruler of Damascus. Among his many inventions, Al-Jazari is particularly renowned for his ingenious clock, known as the elephant clock. Al-Jazari's contributions to Islamic horology were monumental, and his influence on subsequent generations of scientists and engineers was profound. The astrolabe is an intricate astronomical instrument used for navigation, determining time, and making astronomical measurements. The astrolabe consists of several key components, including a central disk called the which is marked with the signs of the zodiac and other astronomical information. The working principle of the astrolabe is based on the apparent motion of celestial objects as observed from Earth. It is important to note that the astrolabe is a complex instrument that requires knowledge of astronomy and mathematics to operate effectively. Let us now take a closer look at one of the most well-known astrolabes from the Islamic Golden Age, the Samat al-Jusiera is an impressive example of the complexity and precision achievable during the Islamic Golden Age. One of the remarkable aspects of this astrolabe is its ability to calculate the positions of stars and planets, allowing for accurate astronomical observations and predictions. What's more, the Samat al-Jusiera is not just a scientific instrument, but also a work of art. Overall, the Samat al-Jusiera stands as a symbol of the Golden Age, representing the pinnacle of Islamic horology. I hope you enjoyed learning about the Islamic Golden Age and the incredible inventions and discoveries of Muslim scholars, and if you're interested in supporting our channel, consider becoming a member. So last week we talked about how clockmaking developed in China, and in particular the fascinating escapement mechanism that made it possible. And then we got a bunch of comments pointing out that, hey, actually that escapement mechanism was invented independently a couple of times by other cultures, including the Arabs and Europeans. So let's talk about how Europeans made clocks. As with any good history story, there are multiple, equally valid ways to start. It is not quite as simple as saying that someone decided to make a clock instead of an automatic bell ringer, but it was almost certainly weight-driven and may have been directly descended from those earlier bell-ringing systems. In fact, until the 18th century, the main clock at Westminster, England, known as Big Ben, was a chime clock, meaning that it rang a chime of bells to indicate the time. And the tradition continues to this day. Someone still has to manually ring the bells. As clocks became more precise, the problem of uneven weights became less significant. you might remember the verge escapement from last week's video. It was the escapement mechanism used in the Chinese clocks. Its motion is heavily influenced by gravity. This made them somewhat inaccurate in the best of circumstances, but nearly useless on a ship. For someone wanting to navigate the seas, having a reliable clock was of paramount importance. We'll tell you who finally solved this problem and how they did it next time. And thank you for watching. But while he was not the inventor, Peter Eng was the first person to use the verge escapement in a spring wound clock. These clocks were portable and accurate enough to be used as personal watches, hence the name Nikan Arm, which literally translates to Nick's arm clock. Henlin's clocks were extremely successful and formed the basis for clockwork watches for the next 2 centuries. As a result, most of the earliest clocks, including those that featured escapements, were what we would today call spring wound clocks. That is, instead of hanging weights, they had springs that would unwind to drive the clock. While these were much more convenient than weights, springs tend to be less reliable. To make matters worse, springs are also rather delicate and susceptible to things like temperature changes, but many clocks, including Big Ben, were designed to ring their bells every hour without human intervention. This was done with a set of weights, cams and pawls, which would engage whenever the clock reached the top of the hour. The only downside was that it required someone to climb up into the clock tower and wind the weights back up every so often. To find out, stay tuned for part 8 of our series on the history of clocks. Coming soon, the first is the story of how something was made. Like last week's episode about how the Chinese made clocks, the second is the story of how the thing spread from place to place, and the third is the story of how the thing evolved once it arrived somewhere new. These are all fundamentally stories about trade routes, but they're stories about a lot of other things too. Stories about religion, politics, war, family, culture. All of this stuff is important and interesting, and I love talking about it. And yet I've spent the better part of the last decade writing grants for science, museums, and educational organizations, trying to find the right words to convey my excitement about these topics to grant reviewers who often do and share my enthusiasm. Since it didn't have an escapement mechanism like the Chinese clocks we looked at last week, it probably kept time by letting a heavy weight fall. Since the weight would descend at roughly the same speed, regardless of the position of the weight, this would result in fairly regular intervals between strikes. They may have also used an escapement mechanism similar to the Chinese, but if so, we don't know what it looked like. These 2 inventions came about for different reasons, in different places, and gradually merged over time. What it does show us is that when Europeans did begin building freestanding clocks, they too began with weight-driven mechanisms. Of course, weights aren't exactly convenient. I mean, who has time to haul buckets of them up a tower every day? This is where our old friend escapement comes in. The problem that escapement was originally designed to solve was that weights fall at different speeds, depending on their height. If you let a weight rise as high as possible and then drop it, it will descend more quickly than if you hold it close to the ground and release it. This means that if you're using a weight to power a clock, you need to periodically reset it, or else it will lose time. Escapement was a way of doing this reset automatically. By using an oscillating weight, you could keep the weight close to the ground most of the time, but allow it to rise a bit when it was necessary to move the hands. In theory, this should prevent the clock from losing time. For this one, though, I think we'll begin with monasticism. See, monks were big on routines. The earliest of these we know about was built in the monastery of St. Gallen in Switzerland, sometime before 997 AD, by a monk named Gerald of Aurillac. We don't know exactly how his automatic bell ringer worked, but it was water-powered, likely with a water wheel driving a series of weights, which would then strike the bells at the appropriate times. Unfortunately, The original version seems to have been destroyed in a fire, but they rebuilt it and it worked for several hundred years. Later versions of the system used falling weights to drive a cam, which would then ring the bells. This design also became very popular in Italy. By the 14th century, the Great Bell Tower of Florence was equipped with such a system to ring its bells for the canonical hours. In particular, they liked to set aside specific hours of the day for prayer, and monasteries typically had bells to call the monks together for these prayers. So far, so good, you might be thinking. Who doesn't like bells? What's the problem? Well, being a monk apparently meant you weren't allowed to have a watch or a phone. So if you wanted to know what time it was, you couldn't just check your Apple Watch. You needed to see the bells, but you probably didn't want to get up for that, so somebody would need to sit and watch the bells. And while that wasn't an onerous duty, assigning someone to sit and do nothing for hours every day can be, well, inconvenient. This is the reason why some of the earliest records we have of people making clocks aren't really records of them making clocks, but records of them making contraptions to ring bells automatically. Okay, but all of this still doesn't explain how they made clocks. The earliest undisputed tower clock was installed in the tower of the Strasbourg Cathedral in 1326. We don't know exactly how this clock worked. Strangely enough, even after the invention of mechanical clocks, bells remained an important timekeeping device. In any case, for several centuries, weight-driven clocks were the primary means of keeping time across Europe. Unfortunately, though none of the early escapements proved entirely reliable. The first major innovation in escapement technology came around 1480, when a German clockmaker named Peter Henlein created the verge escapement. As useful as the verge escapement was, though, it had one fatal flaw. So why did the Chinese develop a superior escapement mechanism, but then never build watches? Okay, so here's the deal. There are 3 parts to this story. If you want to help me learn more about how to talk about history to everyone, you can sign up at the link below. Leonardo da Vinci is one of those rare people whose talents and interests transcended any narrow definition of genius. A painter, sculptor, inventor, scientist, engineer, and architect, he epitomized the Renaissance ideal of the polymath. And today we're looking at 7 of the greatest precision tools ever made by Leonardo da Vinci. The year is 1482, and Leonardo has just moved to Milan. In his notebook, he describes a clock small enough to fit inside a ring, capable of measuring time down to the minute. Leonardo was particularly fascinated with a type of device known as an astrolabe. Again, no physical example survives, but several drawings do, showing its construction and function. Like his other designs, it uses a wheel-based differential gear to transfer motion from the main drive to the rotating plates, allowing multiple displays to be synchronized. It would have been highly accurate, able to calculate the position of celestial bodies within a few seconds of the actual event. These allow him to analyze the structure and movement of the subject more easily, later filling them in with shading and detail. One of these was the egg clock, an intriguing concept that combined horology with art. Additionally, the inclusion of a glass window invited viewers to appreciate the beauty and complexity of the clockwork mechanism, blurring the line between functionality and aesthetics. This unusual device, sometimes referred to as a flying platform, was inspired by the flapping motion of a bird's wings. By studying and attempting to replicate the flight mechanisms of birds and insects, Leonardo was laying the groundwork for future inventors and engineers. His meticulous observations and detailed drawings of avian anatomy and aerodynamics would influence later developments in aviation and serve as a foundation for the eventual realization of powered flight and Leonardo believed it could be replicated to create a human-powered aircraft capable of sustained flight. Ornithopters typically consists of two sets of wings attached to a central frame, resembling the outspread wings of a bird or an insect. The user would manipulate cranks and levers to flap the wings, generating lift and propelling the ornithopter forward. Leonardo's fascination with flight led him to explore various concepts related to the ornithopter, including the study of bird and insect wings, as well as the properties of air and the forces of lift and drag. While no physical examples of Leonardo's egg clocks survive today, his detailed drawings and writings provide valuable insights into this unusual and captivating invention. These detailed illustrations demonstrate Leonardo's meticulous attention to detail and his ability to visualize complex mechanisms in 3 dimensions. Through his drawings, we can see the intricate workings of the egg clock, from the delicate balance wheel to the winding key, providing a tangible connection to this fascinating invention. Leonardo's design consisted of a hollowed-out ostrich egg with a clockwork mechanism placed inside. The egg was then mounted on a stand, often decorated to resemble a bird's nest, and a small glass window was added to reveal the intricate workings of the clock. This created a unique and delicate timepiece that served both as a practical tool for measuring time and a beautiful object of art. This approach allowed him to achieve a level of realism and accuracy that had never been seen before, capturing the movement and weight of the horse, as well as the details of its anatomy. Unfortunately, like so many of Leonardo's works, the statue was never completed, likely due to the complexity of the engineering challenges involved. But the surviving drawings offer us a glimpse into the mind of one of history's greatest geniuses. Its sophisticated design showcases Leonardo's skill as an engineer and his desire to understand the complexities of the natural world, found throughout the ancient world. The astrolabe was originally a simple tool for telling the time by measuring the position of the stars, but it evolved into a complex instrument used to predict astronomical positions. Known today as the Duomo clock, it was installed in the Florence Cathedral in 1494, just 2 years after the astrolabe's completion. Measuring almost 6 feet in diameter, it was one of the largest clocks in Europe and featured innovative designs, including the first known depiction of a differential gear. While not fully functional, it captured the imagination of the public and established Leonardo as a master of mechanics. Through a series of gears, tables, and plates, the astrolabe could display the positions of planets, sun and moon, even predicting eclipses, but he quickly realized that such a project would require more time than he has available. Instead, he designs a bronze monument and promises to complete it in a single night. The centerpiece of the monument is an equestrian statue of Charles VIII, which the king intends to place in the middle of the Seine River. Although the statue was never built, several drawings survive, giving us insight into Leonardo's creative process and the advanced techniques he employed. It was a marvel of engineering, showcasing the knowledge and skills of its maker. This is likely a theoretical design, but it shows his desire to miniaturize clocks and make them more accessible. During his lifetime, pocket watches are large and cumbersome, and many wealthy nobles hire servants to carry them around, so that they can tell the time during important meetings and events. So while no evidence exists that Leonardo ever built a ring watch, his ideas about smaller timekeeping devices live on in the centuries that follow, particularly in the development of the spring-powered watch. Here, the wealthy and influential Visconti family are eager to employ him not only as an artist, but also as an engineer and scientist. They task him with designing a bronze horse for their piazza, and in preparation, they send him to Florence to study a famous bronze horse statue created by the great artist and engineer, Andrea. It's there that Leonardo makes a series of detailed studies and sketches of the horse, which he then takes back to Milan. While he never completes the commission, likely due to the complex mechanics involved. These studies show his interest in equines and his ability to capture motion through careful observation and accurate measurement, and his ideas and designs continue to inspire more than 500 years after his death. In this series, we're taking a closer look at some of Leonardo's most fascinating inventions, discoveries, and insights. But there's something else going on here, too. Something much smaller than the horse itself. His notebooks from this period contain some of the earliest surviving depictions of a spring-driven clock. Until now, all known examples of spring-driven clocks are found in ancient Greece, nearly 1,000 years earlier. But instead of just replicating them, Leonardo improves upon them. His version is not wound up like a modern clock, but rather it has a crank handle to win the mainspring, and its escapement or regulator has a unique design, allowing the gears to spin only when released by the energy stored in the spring. This makes it a true mechanical clock, freed from the limitations of water or weight-driven counterparts. But spring-driven clocks were never Leonardo's true passion. He was far more interested in portable timekeepers that could accurately measure fractions of an hour. As the Medici family rose to power in Florence, they brought with them a renewed interest in classical antiquity, commissioning artists and scientists to study and replicate Roman artifacts. Taking inspiration from these ancient instruments, Leonardo designed his own However, the astrolabe was only the beginning of his work in astronomy. Soon, he would move on to something much larger, the astronomical clock. As he moves to France, the king requests that he design a new tomb for the recently deceased King Charles VIII. He breaks down the subject into geometric forms, reducing the complexity of the horse and rider to basic shapes. Spring-driven clocks captivated Leonardo's imagination, leading him to design several different types of clockwork devices. The egg clock showcased Leonardo's mastery of miniature engineering, requiring precise and delicate craftsmanship to create a reliable timekeeping device that could function within the confines of an egg. One of the most enigmatic inventions attributed to Leonardo da Vinci is the flying machine known as the ornithopter. While the ornithopter never achieved successful flight, it represents a significant step in the history of aviation. If you enjoyed this video, please take a second to subscribe. Thank you for watching. The birth of the pocket watch is a pivotal moment in the history of timekeeping. It marked a significant shift from the large, unwieldy clocks that dominated the 15th century to smaller, more portable devices that could be carried on one's person. But it wasn't just about size. The pocket watch represented a leap in precision. Nuremberg, located in southern Germany, was renowned for its skilled craftsmen, particularly in the production of intricate and delicate mechanical devices. Meanwhile, Geneva, situated in the heart of Switzerland, had become a hub for watchmaking due to its skilled artisans and the abundance of high-quality components and reliability, making it an essential tool for navigation, business, and the burgeoning world of science. In fact, it was probably more of a collaboration between various scientists and engineers over several years. These early watches were simple devices compared to the intricate timepieces of today, but they marked a significant leap forward in portability and accuracy. When the king became enamored with the idea of a portable clock, Henlein crafted a small clock with a spring motor encased in a wooden case that could be carried with a chain or cord. Although no longer in existence, this clock was an early example of the practicality and appeal of a pocket watch. Made from wood ornately carved and inlaid with precious metals, they were status symbols owned by the wealthy elite. Yet, despite any disputes over who truly invented the pocket watch, both Henlein and Galileo shared a common goal: creating a compact and accurate timekeeping device. In 1759, he developed a pocket marine chronometer that could keep accurate time at sea. The increased precision enabled by the balance spring allowed for the mass production of goods and the synchronization of workers' clocks, which was crucial for the efficient operation of factories and machines. This invention earned him a place in history and contributed significantly to Britain's naval supremacy. As these timekeepers became more affordable and accessible, they were adopted by the middle class and eventually the general public. This democratization of timekeeping allowed individuals to carry a piece of luxury on their person and stay connected to the latest trends and events. Before its invention, early portable clocks were often inaccurate and susceptible to variations in temperature, altitude, and movement, making them unsuitable for precise timekeeping. Many watchmakers continue to produce high-end pocket watches that combine traditional craftsmanship with modern technology. Created by the legendary watchmaker Abraham Louis Brigot, this pocket watch is considered one of the greatest ever made. Completed in 1843, the Henry Graves pocket watch features an intricate design with numerous complications, including a perpetual calendar, minute repeater, and a unique equation of time display. These timepieces are not only functional, but also serve as wearable pieces of art. With everyone relying on these portable devices, there was a need to ensure that all clocks were synchronized. This resulted in the creation of time zones, which facilitated communication and travel across vast distances. In this episode, we'll explore how these fascinating inventions came into existence during the 16th century, who were the masterminds behind them, and what role they played in shaping our relationship with time. The watch is also notable for its exceptional accuracy, a testament to Brigot's dedication to precision timekeeping and craftsmanship that went into each tick-tock, reminding us of the enduring legacy of this iconic invention. If you have any questions or comments, please feel free to leave them below. We love hearing from our viewers and appreciate your feedback. Its regular and predictable motion made it possible to create more intricate and decorative designs, which became highly sought after by collectors and watch enthusiasts. After changing hands several times, it resurfaced in the possession of a private collector in the United States. With that said, until next time, stay curious and keep exploring the wonders of our world. These masterpieces not only displayed exceptional craftsmanship, but also featured innovative features such as the tourbillon, which further improved accuracy by rotating the escapement and balance wheel. Its intricate design, advanced technology, and fascinating history continue to captivate those who admire the finest examples of watchmaking. This astronomical figure underscores the value and rarity of this exquisite timepiece. Master clockmakers like Joster Bergy and Abraham Louis Perlet in Switzerland, as well as Christian Huygens in the Netherlands, started experimenting with the concept, and by the late 17th century, pocket watches had become commonplace among the upper classes. It has shaped our relationship with time, influenced the course of scientific discovery, and served as a constant companion throughout the ages, which were more convenient and less prone to damage than pocket watches. While pocket watches are no longer as prevalent as they once were, they remain coveted collector's items and symbols of a bygone era. By minimizing these errors, the balance spring paved the way for more accurate marine chronometers, which were essential for long sea. This innovation had far-reaching implications for exploration, trade, and military operations. Legend has it that while working on a commission to create a small alarm clock for a wealthy patron, Henlein stumbled upon a solution to this age-old problem. He realized that by incorporating a balanced wheel, a component used in clocks to regulate the release of energy, he could significantly improve the accuracy of a portable timepiece. By the 16th century, Nuremberg and Geneva had established themselves as centers of horological expertise. However, there was a missing piece in the puzzle. The clockmakers of Nuremberg had mastered creating large, impressive timepieces. But as the name suggests, their clocks were typically so large that they couldn't be carried around. His goal was to create an accurate portable clock that could withstand shocks and temperature changes, which were common issues with early portable clocks. He also wanted it to be precise enough to measure time intervals for scientific experiments. They needed a way to miniaturize their creations without sacrificing accuracy. Enter Peter Henlein, a locksmith from Nuremberg. On the other hand, Galileo Galilei was independently working on a similar concept in Italy. Though historians debate whether Galileo actually invented the first pocket watch, his contributions were instrumental in its development. And as we mentioned before, Henlein is credited with producing the first series of portable spring-powered watches in the 1540s. One of Henlein's notable creations was commissioned by Henry VIII of England. As word spread of these incredible new timekeepers, demand began to grow. Meanwhile, the balance spring was a revolutionary addition that significantly improved the accuracy and reliability of pocket watches. The balance spring, a small, flexible metal strip attached to the balance wheel, addressed these issues by providing a more consistent and reliable source of energy. For instance, John Harrison, an English clockmaker, dedicated his life to improving marine chronometers. Beyond its impact on navigation, the balance spring also played a vital role in the Industrial Revolution. But it wasn't just about functionality. The balance spring also contributed to the aesthetic appeal of pocket watches. In the 18th and 19th centuries, Swiss watchmakers such as Abraham Louis Breguet and John Arnold created some of the most exquisite pocket watches ever seen. The rise of pocket watches also had profound social and cultural implications. The widespread use of pocket watches also led to the standardization of time. However, as the 20th century progressed, technological advancements led to the development of wristwatches. Today, the legacy of the pocket watch lives on in the world of horology. But the story doesn't end here. One remarkable pocket watch, the Henry Graves pocket watch, holds a special place in horological history. Commissioned by Henry Graves, an English watch collector and connoisseur, the watch was designed to showcase Breguet's finest craftsmanship and innovative techniques. Its back is adorned with an enameled painting depicting a mythological scene, further highlighting the artistry involved in its creation. But the story of the Henry Graves pocket watch took an unexpected turn when it disappeared in the early 20th century. In 2014, the watch was sold at auction for a record-breaking price, fetching nearly $24 million. For watch collectors and enthusiasts, the Henry Graves pocket watch remains a symbol of excellence in horology. From its humble beginnings in Nuremberg and Geneva to its evolution into a global phenomenon, the pocket watch has left an indelible mark on human history. As we look back on the remarkable journey of the pocket watch, we can appreciate the ingenuity. We hope you enjoyed this episode and learned something new about the fascinating world of pocket watches. And if you haven't already, we invite you to subscribe to our channel and join our community of curious learners. How do we measure 1 second? We can all tell you it's the 60th part of a minute. But how long is a minute? And where did our modern concepts of timekeeping come from? From the mid-19th century onwards, factories were springing up all over the industrialized world. They were loud, dirty, and dangerous places to work. Railways depended on precision in scheduling, and missed connections could lead to angry passengers and lawsuits. This required the development of more precise timekeeping methods and instruments. But why did trains need such precise timetables? After the introduction of the telegraph, communication across the Atlantic was immediate. To synchronize the clocks in Europe and America, the British took the solar time at Greenwich and added 1 hour. Well, the Earth's rotation causes a time difference of approximately 4 minutes between Greenwich and Paris. Pendulums have been used as timekeepers since when they were first described by Dutch scientist Christian He. They vibrate at a constant frequency when an electric current is applied. In particular, they utilize the cesium atom, which vibrates at a very precise frequency when exposed to electromagnetic radiation. Photons are the smallest possible unit of light, and they travel at a constant speed. By shining a beam of light onto a detector and counting the number of photons that hit it in a given amount of time, we can accurately measure time. This method is known as photon counting, and it is extremely precise. It has become the preferred method for measuring time in some applications where extreme accuracy is required. In fact, it is so precise that it can measure the passage of time down to the trillionth of a second. By counting the number of vibrations, atomic clocks can keep incredibly accurate time. Time may be a human construct, but we continue to push the limits of how precisely we can measure it. Maybe one day we'll be able to measure time down to the quantum level. Until then, we'll just have to settle for our trusty atomic clocks and the occasional photon counter. Atomic clocks are so precise that they lose only 1 second every 100 million years. That's around 300 times more accurate than quartz crystal clocks. They are used as the world's primary time standard, ensuring that time is kept as accurately as possible. But what about the smallest second of all? This means that they can be used to create highly precise clocks and watches. The vibrations of a quartz crystal are much more stable than those of a pendulum or a balance wheel. Furthermore, quartz crystals are durable and low maintenance, making them an ideal choice for timekeepers that require minimal upkeep. Some quartz watches are accurate too, within a few seconds per year, far more precise than mechanical movements. However, for the ultimate in precision, we turn to atoms. Their use of pendulums revolutionized timekeeping. As a pendulum swings back and forth, it does so with a regular and predictable rhythm, making it an ideal tool for measuring time. The length of a pendulum's swing is determined by its length, with longer swings taking longer to complete a full cycle. By carefully adjusting the length of a pendulum, engineers can ensure that it completes exactly 1 cycle every second, providing a constant and reliable beat for a clock or watch. But if you think a pendulum is too simple, wait till you hear about the next way we've kept time. So, adding 1 hour made it only 3 minutes fast. This meant that if your watch was set to Greenwich time, it was almost accurate enough to be used in Paris. Today, however, the situation has changed dramatically. The International Earth Rotation Service monitors the Earth's rotation and decides when to introduce leap seconds. A leap second is an additional second added to the last minute of the day to keep civil time in sync with the Earth's rotation. This keeps the accumulated error of 1 millisecond per century to a minimum. However, sometimes an additional leap second is necessary. This is known as a negative leap second and has only occurred twice since the system was introduced. Well, imagine you're waiting at a train station and 2 trains pull in. First, we need to separate the display of seconds from the mechanism that controls them. While the basic principles of stopwatches have remained the same, their construction has evolved over time. Early stopwatches were large and cumbersome, but advancements in technology and engineering have resulted in smaller, more portable devices. In fact, it was the demand for accurate stopwatches for horse racing that drove many innovations in the field. For example, John Arnold created the first portable stopwatch in 1754, while Thomas Earnshaw invented the anchor escapement in 1826, which is still used in high-quality watches today. In 1881, the keyless winding system was introduced, followed by the monometallic balance spring in 1915, both of which were major advances in watchmaking. The development of the quartz crystal oscillator in the 1960s allowed for even greater accuracy and reliability. This is the device most commonly used in modern digital stopwatches, and is much more accurate than a traditional mechanical movement. This was accomplished by Daniel Quare in 1675, who created the first chronograph. His invention featured a separate dial to display seconds, allowing the escapement to run more smoothly without being affected by the weight of the second's hand. This separation allowed for more accurate timekeeping and paved the way for further improvements in chronographs. But a chronograph is not the only way to measure a second. One's late and the other's right on time. If they both depart at the same time, then the late train will overtake the early one. You can see the problem here. Trains have to be synchronized to ensure the safety of passengers and goods. In 1857, the Liverpool and Manchester Railway set the average time of their 37 clocks at 1 minute past the time of the sun. As apparent motion across the sky known as solar time at the Royal Observatory in Greenwich, England. This was done to allow the trains to arrive and depart from stations accurately. However, it wasn't until the railways spread to the rest of the country that this became an issue. You see, although the Earth is round, local times differed significantly from region to region due to slight variations in longitude. On a train journey from London to Birmingham, a passenger might experience 5 different local times in a single trip. It was clear something had to be done. So, in 1884, the railways met with astronomers and watchmakers and drew 4 standard lines of longitude across the United States. They divided the country into 5 time zones, one for each line of longitude, and an additional zone for the North Pacific coast. This solved the problem of coordinating railway timetables across the country, but it did cause another problem. For the first time in history, people were working together in large numbers under one roof. Enter the time zone map. But wait a second, if you live in the Eastern time zone, don't you actually live in the 4th time zone counting from Greenwich? Well, yes, but we tend to count from the prime meridian line passing through Greenwich, going east to Australia and New Zealand, which are 12 and 13 hours ahead, respectively. Going west, we pass through the Azores and then the various time zones of the Americas. When it's noon in Greenwich, it's midnight on the west coast of the US and 6 p.m. on the east coast. Despite these changes, the concept of universal time remained consistent. As the Earth rotated, time moved inexorably forward. That is, until someone came along and decided it should move even faster. This brought with it a whole host of problems, not least of which was keeping track of time. How could a supervisor keep track of 100 workers all doing slightly different jobs and keep them all on the same schedule? Well, they needed a system, and what better way than factory bells? Big bells would ring out every quarter hour, reminding workers to get back to work after their break or to mark the start and end of their shift. These bells also provided a sense of community for the workers, a regular reminder that they were all in it together. They were like the old town criers, only instead of making announcements, they were just ringing a bell. In the US, many states had laws passed requiring factories to stop production for 15 minutes each day, so that all the workers could attend prayer. Even though this law was eventually overturned by the Supreme Court, the practice continued in some factories. Let's take a look at how the humble second came to be. But due to a series of technicalities, no fewer than 12 Acts of Parliament were passed before proper regulations came into effect in 1844. The workshop of John Joseph Merlin in Bristol was among the first to adopt a time clock in 1840. The US saw its first factory clock installed in a Connecticut textile mill in 1845. Although these clocks did not usually strike, they did chime at the half hour to remind the workers of the time. The clocks were synchronized with the local mean time and were considered incredibly accurate at the time. though because of the variation between local mean times, there was still a problem in synchronizing clocks across the country. The solution to this problem led us to our next point. Number 10. Industrial timekeeping. In Britain, Parliament attempted to regulate factory hours and working conditions as early as 1833. Number 9. Railway timetables. Before the advent of computers, when trains became popular in the mid-19th century, having accurate timetables and timepieces was essential. Number 8. Time zones. Now that there were 5 time zones in the US, how did you know which one you were in without checking the longitude? Number 7. The global clock. Number 6. Chronographs. Now that we have our time zones, let's see how we can accurately measure a second within them. Number 5. Stopwatches. Stopwatches are unique because they can be stopped and started at will, allowing for extremely precise timekeeping. Number 4. Pendulums. Number 3. Quartz crystals. Quartz crystals have become the most common timekeeping element in modern times because they are so accurate. Number 2. Atomic clocks. Atomic clocks are the most accurate timekeepers ever created. They use the vibrations of atoms to measure time. Number 1. Photons. Believe it or not, we can measure a second by counting photons. There you have it. A quick breakdown of how we measure 1 second. This is part 10 of our series on the history of timekeeping. In this installment, we'll look at industrial timekeeping, the origins of time zones, chronographs, and stopwatches. And so timekeepers were needed that could accurately indicate the time without relying on natural light. They allowed passengers to know exactly when to arrive at stations and enabled railway staff to manage the complex logistics of running multiple train services simultaneously. Historically, there have been numerous methods for measuring short intervals of time, but the chronograph is a standout instrument designed specifically for this purpose. The most common type of chronograph is the wrist chronograph, which typically features a circular face with 3 small dials. These inventions have had a significant impact on various aspects of our lives, from manufacturing processes to sports and project management. As technology advances, we continue to see improvements in accuracy, convenience, and functionality in timekeeping devices. These subdials display the seconds, minutes, and hours elapsed during the measurement period. If you liked this video, please hit the thumbs up button and subscribe to our channel for more captivating content. Additionally, a central hand is used to measure the seconds for the chronograph function. The stopwatch mechanism typically includes a winding mechanism to power the timekeeping function and a key or button to wind the watch. The key or button also serves to start and stop the chronograph function. When activated, the chronograph seconds hand sweeps around the dial at a constant rate, allowing for the measurement of elapsed time intervals. The minutes and hours subdials accumulate values based on the duration of the measurement. Stopwatches often have a more compact design compared to they usually feature a single hand that moves around the dial to indicate elapsed time. Some stopwatches may include additional features such as split time functions or timers. These functions allow users to measure multiple time intervals concurrently or set short-term goals. Stopwatches have practical applications in various contexts, including sports, cooking, and project management. In sports, they're used to time events or track athletes' performance. For cooking, they help measure baking or cooking times. In project management, stopwatches assist in monitoring progress and allocating time effectively. Some stopwatches offer water resistance or shock resistance, enhancing their durability. More advanced models may incorporate digital displays for precise time readings. A chronograph is a timepiece that includes a mechanism for measuring elapsed time, typically featuring a second hand that can be activated and deactivated independently of the main timekeeping mechanism. Its purpose is to measure the duration of events, calculate speed, or perform other tasks requiring precise time measurements. Stopwatches are portable devices used to measure elapsed time. They have a distinct design with a circular face and a mechanism to start, stop, and reset the timekeeping function. Stopwatches are commonly used for timing events, measuring durations, or setting short-term goals. Throughout history, various cultures have employed diverse techniques to measure time intervals. Ancient civilizations used water clocks and sundials as rudimentary timekeeping tools. However, with the evolution of technology, more sophisticated methods were developed. During the Middle Ages, mechanical clocks incorporated features like chimes and bells to mark specific time intervals. The Industrial Revolution spurred innovations such as precision timepieces and chronographs used in manufacturing processes. Today, quartz watches and atomic clocks offer highly accurate timekeeping, while smartwatches and mobile devices provide convenient access to time measurement functionalities. With the increasing importance of accurate timekeeping came the need for standardized measurement across long distances. Before the 19th century, time was often measured locally and could vary significantly from place to place. However, the invention of the telegraph enabled communication of precise time signals over long distances. The synchronization of clocks using telegraph signals helped establish uniformity in timekeeping. One notable system was the Royal Observatory's time signal at Greenwich, England, which was widely adopted and disseminated through telegraph networks. With the development of railways, the need for synchronized clocks extended beyond local areas. Railway companies established timetables that listed departure and arrival times for trains at various stations. These timetables not only helped passengers plan their journeys, but also allowed railway staff to coordinate the movement of trains across vast networks. The standardization of time zones became increasingly important as transportation and communication systems expanded. The absence of synchronized clocks led to confusion and delays. People traveling by train or ship would face challenges in coordinating schedules due to the lack of a standardized timekeeping system. To address this issue, several initiatives were undertaken to establish consistent time zones across regions. Notable efforts included the adoption of coordinated universal time at the Paris Meridian and the introduction of standard time zones in the United States by railroad companies. These developments laid the groundwork for the global clock system we use today. The establishment of time zones allowed for more accurate and consistent timekeeping across different regions of the world. By dividing the Earth into 24 time zones, each spanning 15 degrees of longitude, the global clock system ensured that there was minimal variation in time measurements between locations. This standardization facilitated communication, transportation, and other activities that required precise time coordination. It is interesting to note that the standardization of time has had a profound impact on various aspects of human life, including sleep patterns, metabolism, and even the stock market. Our bodies have internal clocks known as circadian rhythms, which help regulate sleep-wake cycles and other biological functions. However, with the advent of artificial lighting and non-aligned work schedules, our circadian rhythms have been disrupted, leading to potential health issues. Additionally, the global nature of financial markets has contributed to a homogenization of sleep patterns, with people in different time zones often sacrificing sleep to participate in global economic activities. Furthermore, the stock market operates on a tight schedule with trading hours and reporting deadlines adhering to specific time zones. This creates a sense of urgency for investors and market participants who need to make decisions within narrow timeframes. So next time you check your watch or phone, take a moment to appreciate the intricate mechanisms and historical developments that have brought us the gift of accurate timekeeping. Various mechanical devices such as wheels, balancers and pendulums were used to regulate the motion of the hands on the clocks. Early time clocks often took the form of large, elaborate devices mounted on walls or placed on tables. They served as visual reminders for workers to stay on schedule and complete their tasks efficiently. As manufacturing processes became more complex, there was a growing demand for more precise and consistent time measurements. This led to the development of specialized timekeeping instruments such as chronographs and stopwatches. There were no dedicated timepieces for the wrist until the early 20th century. Before that, people carried pocket watches, which was quite an inconvenience, since they had to be pulled out of one's pocket to tell the time. But what about when you need both hands for other tasks? Or if your pockets are too full? For example, during the Industrial Revolution in the 19th century, factory owners sought to improve efficiency by introducing the concept of time clocks. These clocks would not only keep workers on schedule, but also ensure that products met strict quality standards. The standardization of time was crucial for the synchronization of machinery and production processes. You can still see some of these old clocks today in factories and workshops. Their purpose was to manage human labor rather than to measure astronomical phenomena. Before the advent of reliable timepieces, people relied on the sun for timekeeping. But with the rise of industrialization, people started working indoors. Railway timetables were introduced to coordinate the schedules of trains and ensure punctuality. Let's now turn our attention to chronographs and stopwatches. Early chronographs often utilized a separate escapement and mechanism to drive the chronograph seconds hand, allowing it to run independently of the timekeeping function. It's fascinating how timekeeping innovations like chronographs and stopwatches have evolved. Alongside industrialization and our need for precise measurements, that's it for today's episode. Let us know in the comments below which aspect of industrial timekeeping intrigued you the most. Wristwatches and personal time, a pocket watch on your wrist. In the early 20th century, armed conflicts dominated Europe. The First World War raged, and new technologies emerged to aid soldiers in the heat of battle. Enter the wristwatch, a convenient alternative to the pocket watch that had been the standard for centuries. This innovative timepiece was designed with practicality and functionality in mind, featuring a metal band that could be attached directly to a soldier's uniform, eliminating the need for a pocket or fob chain. Before proceeding to the video, don't forget to subscribe so you won't miss the latest tech updates. The G-Shock GW9400 Rangeman is a rugged and versatile timepiece designed for outdoor enthusiasts and adventure seekers. With its shock-resistant structure and water resistance up to 200 meters, this watch can withstand the toughest conditions. It features a round, stainless steel case and a leather strap, giving it a timeless appeal. The watch has a high-quality quartz movement, ensuring accurate timekeeping. The silver-colored dial with black Roman numeral displays a clean and minimalistic aesthetic, while the signature Tissot logo adds a touch of sophistication. The T1274071105100 is water-resistant up to 30 meters, making it suitable for everyday wear. It features a unique tonneau shape, inspired by the car's sleek design. The watch has a black ceramic case and a black rubber strap, giving it a bold and sporty look. The dial displays a captivating blue and orange color scheme reminiscent of the car's livery. It features a round stainless steel case and a stainless steel oyster bracelet, known for its durability and comfort. If you're interested in tech, subscribe to our channel. The watch has a black dial with luminous hands and markers, offering excellent legibility underwater. Until then, peace out. Powered by Rolex's perpetual movement, It provides precise timekeeping and is certified as a chronometer. The Submariner also features a date display window and a unidirectional rotating bezel with a sapphire insert. With its water resistance of up to 300 meters, it is suitable for professional diving. The watch is also available in various precious metals, including yellow, white, and Everose gold. Whether you're exploring the depths of the ocean or dressing up for a special occasion, the Rolex Submariner is a timeless and iconic choice. Powered by the Unico to Hublot movement, it offers exceptional chronographic functions and precise timekeeping. The watch also features a date display window and a bidirectional rotating bezel. With its 500 limited edition status, the LaFerrari Micro Racer is a highly sought-after timepiece for collectors and car enthusiasts alike. It is also equipped with a date function for added convenience. It features a round stainless steel case and a comfortable leather strap, giving it a classic and sophisticated look. The watch has a black dial with silver hands and markers, offering a clean and minimalistic aesthetic. Powered by Citizen's EcoDrive technology, it harnesses the power of light, eliminating the need for battery changes. The Corso also features a date display window and a reliable quartz movement. With its water resistance of up to 100 meters, it is suitable for swimming and snorkeling. Whether you're redressing up for a special occasion or adding a touch of elegance to your everyday attire, the Citizen Corso is an excellent choice. This watch is presented in an attractive gift box, making it an ideal choice for special occasions or as a corporate gift. It features a round stainless steel case and a stainless steel bracelet, giving it a classic and sophisticated look. The watch has a black dial with silver hands and markers, offering a clean and minimalistic aesthetic. Powered by Omega's renowned 300 caliber movement, it ensures precise timekeeping and durability. The Seamaster 300 is also equipped with a date display window and a unidirectional rotating bezel. With its water resistance of up to 300 meters, it is suitable for scuba diving and other aquatic activities. Whether you're looking for a dress watch or an adventure companion, the Omega Seamaster 300 is a versatile and reliable choice. The GW 9400 Rangeman features a large digital display that provides easy visibility in any lighting conditions. It offers various functions such as an altimeter, barometer, compass, and thermometer, making it a valuable tool for outdoor activities. The watch also has a countdown timer, 5 daily alarms, and a chime function. Its comfortable resin strap ensures a secure fit on the wrist, while its solar-powered technology eliminates the need to change batteries. Whether you're hiking, camping, or simply looking for a durable everyday watch, the G-Shock GW 9400 Rangeman is a reliable companion. Soldiers embraced this new invention, as it allowed them to keep their timepiece close at hand while carrying out their duties. The wristwatch quickly became an essential tool on the battlefield, providing soldiers with accurate timekeeping abilities during the chaos of war. The Casio G-Shock 5610 U1 is a stylish and functional smartwatch that combines classic design with modern technology. It features a retro square face and a resin strap, giving it a timeless appeal. The watch has a mineral glass display that is resistant to scratches and easy to read. Powered by solar technology, it eliminates the need for battery changes and automatically adjusts the time in multiple world time zones. It also includes a countdown timer, 5 daily alarms, and a chime function for added convenience. With its durable construction and water resistance of up to 200 meters, this watch is suitable for a wide range of activities. Whether you're engaging in outdoor adventures or simply looking for a reliable timepiece, the Casio G-Shock GWM 5610 U1 is a great choice. After the war, This trend continued and wristwatches evolved into an essential part of everyday life for people all over the world. As time went on, these accessories reflected the latest trends in fashion and design. The interwar period gave rise to the Art Deco movement, which emphasized clean lines and geometric patterns. This influence can be seen in watch designs of the time, which often featured square or rectangular faces with bold hands and Roman numerals. Renowned brands such as Rolex and Omega incorporated these elements into their timepieces, creating iconic models that continue to be coveted by collectors today. The quartz revolution marked a significant advancement in watchmaking history. In the 1960s, battery-powered accuracy and reliability transformed the industry forever. Seiko, a Japanese brand, pioneered the use of quartz movements in wristwatches, offering consumers an affordable alternative to mechanical timepieces. These watches were not only highly accurate, but also low maintenance, requiring little more than a battery change to keep them functioning precisely. Today, quartz watches remain popular among watch enthusiasts who appreciate their dependability and affordability. Here are some of the best-selling wristwatches available on Amazon. Number 10. G-Shock GW9400 Rangeman. Number 9. Casio G-Shock GWM 5610 U1. Number 8. Tissot T127 407 1105 100. The Tissot T127 407 110 510 is an elegant and sophisticated timepiece that exudes classic Swiss craftsmanship. Number 7. Seiko Prospex SAB Coup Hota 01 CAT. The Seiko Prospex SBQ-J017 is a stunning timepiece that combines precision engineering with a sporty aesthetic. It features a round stainless steel case and a comfortable silicone strap, making it ideal for outdoor activities. The watch has a black dial with silver hands and markers, offering a sleek and sophisticated look. Powered by Seiko's renowned 8F56 quartz movement, it provides accurate timekeeping and is resistant to shocks and magnetic fields. The sapphire crystal glass is scratch-resistant and offers a clear view of the dial. The watch also features a convenient date display window. With its water resistance of up to 200 meters, the Seiko Prospex SBQ-J017 is a versatile timepiece suitable for diving and other water sports. Whether you're exploring the depths of the ocean or simply looking for a stylish and durable watch, the SBQ-J017 is an excellent choice. Number 6. Fossil Gen 6. The Fossil Gen 6 is a stylish and feature-rich smartwatch that seamlessly blends fashion and technology. It features a round touchscreen display with a customizable watch face and fitness tracking capabilities. The watch also offers smartphone notifications, music control, and payment services for added convenience. With its slim design and available in various colors, it complements any outfit. The Gen 6 is compatible with both Android and iOS devices, allowing you to stay connected. It includes health sensors that track your activity levels, heart rate, and sleep patterns. The built-in GPS enables you to track your location and distance traveled during your workouts. With a long-lasting battery, you can use the smartwatch all day without worrying about running out of power. Number 5. Longin's Master Collection L8 999 800 16733. 733 is a sophisticated timepiece that embodies timeless elegance and precision engineering. It features a round stainless steel case and a blue leather strap, giving it a classic yet stylish appearance. The watch has a silver-colored dial with gold hands and markers, adding a touch of luxury. Powered by the L888 2 quartz movement, It ensures accurate timekeeping and longevity. The sapphire crystal glass is scratch resistant and offers a clear view of the dial. The watch also features a date display window for added convenience. With its water resistance of up to 50 meters, the L8-999-816733 is suitable for everyday wear. Whether you're attending a formal event or dressing up for a night out, this timepiece is sure to impress. Number 4. Hublot LaFerrari Micro Racer. The Hublot LaFerrari Micro Racer is a remarkable timepiece that pays tribute to the legendary LaFerrari. Number 3. Citizen Corso. Corso. The Citizen Corso is a stylish and eco-friendly timepiece that appeals to watch enthusiasts and environmentally conscious individuals. No, Omega Seamaster 300. The Omega Seamaster 300 is a timeless and elegant timepiece that has been worn by notable figures such as James Bond. Number 1. Rolex Submariner. The Rolex Submariner is a legendary diving watch that has become a symbol of luxury and adventure. Now let's move on to the latest tech news. Hey everyone, this is a representative from an organization, and today we are celebrating the 12th anniversary of an initiative. We're going to talk about atomic time and the digital age. How does the world keep time? What is the role of the cesium fountain? How do we get all the computers in the world to agree on time? How can your computer tell the exact time down to billions of ticks? Why was the second redefined in 1967? There are many different cesium fountains around the world, and their signals are compared to keep time. Computer scientists needed a way to keep track of time digitally, and since computers were going to play an increasingly important role in our society, it made sense to adopt a universal digital time. As a result, the epoch became the starting point of the Unix time counting system. This means that it gains or loses around 200 microseconds of time each day due to both its high speed and the fact that it is farther away from the Earth's gravity. A countdown of 57 seconds minus 25 microseconds equals 53 seconds. Therefore, when the satellite is launched, the clock on board is set to count down for 53 seconds before starting the actual mission. If the launch takes place at TO, the satellite's clock starts counting down from 53 seconds after it reaches 0. The clock is synchronized with the Earth, and it is ready to provide positioning, navigation, and timing services. If the countdown ends during flight, a time offset needs to be applied. In order to maintain synchronization with the Earth-based clocks, the clocks on board the satellites are subject to a time correction of approximately 45 microseconds every 12 hours. As a result, after an orbital period of 12 hours, the clock on board the satellite is only 25 microseconds ahead of the reference clock on Earth. You can also comment below with any thoughts or questions you might have, and if you'd like to learn more about our work, please visit our website. Thank you for watching. At 0 hours, 0 minutes, and 0 seconds, Coordinated Universal Time on January 1st, 1970, this corresponds to the cesium clock counting 10 to the 15 power events. The number of seconds elapsed since the epoch is therefore equal to the number of events counted by the cesium clock divided by 10 to the 15 power. From GPS navigation to computer time stamping, many of these applications rely on the precise measurement of time. As technology continues to advance, the demand for even more accurate and reliable timekeeping will continue to grow. Who knows? Maybe one day we will even have a complete understanding of time and how it works. For example, the Coordinated Universal Time, or UTC, is generated by taking the average of several primary time standards, including those from cesium fountains. These standards are maintained by national metrology institutes such as PTB in Germany and NPL in the UK. Cesium fountains are also used in GPS satellites to keep track of time while orbiting the Earth. Since the satellites travel at high speeds and experience strong gravitational forces, they need to carry onboard clocks that are extremely accurate. These are some of the topics that will be covered. We have 3 topics today, but they are interconnected, so let me introduce them. Let's start with the cesium clock. Of course, we couldn't have chosen any day, because if we had chosen a Sunday, then 1 week would have been longer than 7 days. That would have been bad. So we picked the first Friday to avoid potential confusion. Unix time is measured in seconds from the epoch, and it is used in many operating systems and applications to record and process dates and times. It is also the basis for many programming languages, allowing programmers to perform calculations involving dates and times. Unix time is especially useful when working with large datasets or performing complex calculations, because it provides a consistent and reliable way to handle dates and times. Additionally, Unix time can be converted to other date and time formats using various utilities and libraries, making it versatile for different applications. Overall, the widespread adoption of Unix time has helped to standardize and simplify date and time processing across different systems and applications. For centuries, we used astronomical observations to define the second. This is because the cesium atom has a natural frequency which is incredibly stable. It is independent of external factors like the Earth's rotation, and it is easily measurable. We found that a second is defined as 9,192,631,770 periods of the radiation corresponding to the transition between the 2 hyperfine levels of the ground state of a 133 atom. When atoms are irradiated with microwaves, they absorb energy and jump to a higher energy level. If the frequency of the radiation matches the natural frequency of the atom, resonance occurs, and the atom is said to be excited. By measuring the frequency of the absorbed microwave radiation, one can determine the frequency of the cesium atom. 1 cycle of the wave corresponds to 1 vibration of the atom, and so we have our new definition of the second. First it was the stars, and then the moon, and then the Earth's rotation, and finally we settled for the position of the sun. Once we decided that the day should be divided into 86,400 seconds, it made sense to continue with that definition. Because if the Earth's rotation slows down or speeds up, we don't want to change the length of a day. However, there are more stable ways of defining the duration of a second. In 1967, the second was redefined in terms of a cesium atom. Now, to measure these vibrations, we use cesium fountain. But why did we choose Well, it just so happens that for cesium-133, the energy difference between the 2 hyperfine levels is exactly 9,192,631,770 Hz, which makes it easy to count the number of oscillations to get a second. A cesium fountain is a device used to generate a clock signal based on the natural frequency of the cesium atom. To create a cesium fountain, cesium vapor is produced in a vacuum chamber and then cooled to a few degrees Celsius. An intense laser beam is then pointed at the vapor, and it causes the cesium atoms to be excited. Now we can measure the frequency of the radiation emitted by the cesium atoms, and thus we know the exact time. The accuracy of a cesium fountain is only a few nanoseconds per year. Let's talk now about Unix time. The reason we chose January 1st, 1970 is that it was a Friday. And finally, let's talk about GPS satellites. When a GPS satellite orbits the Earth, it travels at a speed of around 14,000 kilometers per hour. To make up for the remaining 25 microseconds, a countdown is started before launching the satellite, which is stopped once the satellite is operational. So we see that keeping time accurately is important not only for our daily lives, but also for many applications that we take for granted today. If you liked this video, please click the like button and share it with your friends and colleagues. The history of smartwatches has been an interesting one. After all, what is it's a device that's supposed to make life easier by putting key functions at your fingertips. In this video, we will explore how smartwatches have evolved and what the future might hold for this fascinating category of devices. Let's get into it. And yet some of the most popular models have been notorious for being overcomplicated and trying too hard to be more than just a watch. And so, as we stand here today in the dawn of new computing power with AI everywhere, maybe it's finally time for the perfect information was presented in long columns, scrolling vertically. When notifications arrived, they'd slide in from the right side of the screen. However, in June 2016, Pebble's journey came to an end when it was acquired by Fitbit. While the Pebble hardware was discontinued, the software lived on, powering certain Fitbit watch models. They were available in two sizes, 34 and 38 millimeters, catering to different wrist sizes. Today's smartwatches and other wearables are packed with sensors and features that can monitor everything from heart rate to sleep patterns to stress levels. They connect seamlessly with smartphones, allowing users to receive notifications and control apps from their wrist. AI integration is becoming increasingly prevalent, with many smartwatches now capable of analyzing user data and providing personalized insights and recommendations. The combination of advanced sensors, connectivity, and AI is transforming the way we monitor our health, manage our time, and interact with technology. Instead of a conventional watch band, the O-ring is designed to fit comfortably between the skin and clothing, providing a discreet and unobtrusive wear. With a stainless steel case and a high-resolution AMOLED display, it offers users a premium experience. The Watch 3 Pro features advanced fitness tracking capabilities, including GPS, heart rate monitoring, and sleep tracking. It also offers a variety of workout modes and route tracking capabilities. The watch is compatible with both Android and iOS devices and provides users with comprehensive health insights. Experience seamless integration with your smartphone, receiving notifications and controlling music playback with ease. Stay connected and entertained without the need for a bulky Here are just a few examples of the latest and greatest wearables. While the initial versions lacked independent cellular connectivity, relying on the paired iPhone 4 network access, later models gained this capability, allowing them to function even when separated from the phone. From improved health monitoring to new ways of interacting with technology, the possibilities are endless. Whether you're a fitness enthusiast, a tech innovator, or just someone looking to stay ahead of the curve, there's never been a more exciting time to be a part of the wearable revolution. With a sleek design and a rotating bezel, it offers users a premium experience. Or will there be a shift towards specialized watches for specific use cases? Share your thoughts in the comments below. And don't forget to like and subscribe for more updates on the latest tech trends. Thanks for watching, and we will see you in the next one. With a vibrant AMOLED display and a lightweight design, it provides users with a comfortable and stylish wear. With a slim design and a color touchscreen, it provides users with an easy-to-navigate interface. The Charge 6 features advanced sleep tracking, heart rate monitoring, and stress tracking. It also offers a variety of goal-setting tools and challenges to help users stay motivated. The tracker is water-resistant and provides users with up to a week of battery life. The Venue 2 Plus features advanced fitness tracking capabilities, including GPS, heart rate monitoring, and sleep tracking. It also offers a variety of workout modes and recovery insights. The watch is compatible with both Android and iOS devices and provides users with daily readiness scores to help them optimize their workouts. Powered by the Exynos W980 processor, it boasts impressive performance and a sapphire crystal display for durability. The Galaxy Watch 6 Classic features advanced health monitoring capabilities, including ECG, blood pressure, and sleep tracking. It also offers a range of fitness tracking features and long battery life. The Apple Watch's user interface was heavily influenced by iOS, featuring circular app icons and a swipe-based navigation system. The digital crown, a prominent feature of the watch's design, enabled users to scroll through content by rotating it. Additionally, the watch could receive notifications from various apps, including third-party options. Although the ability to respond to these notifications was limited, the first generation of the Apple Watch was powered by the S1 chipset, a custom-designed chip developed by Apple specifically for the watch. The S1 was notable for its low power consumption, a crucial consideration for a wearable device. As of 2015, the Apple Watch lineup included several models with varying sizes and finishes such as stainless steel and titanium. Price points ranged from around $400 for the initial entry-level models to over $1,000 for premium versions with cellular connectivity. The Apple Watch's impact extended beyond its technical specifications. It reflected a broader cultural shift towards wearable technology and the integration of smartphones and smartwatches as complementary devices. The Apple Watch's success paved the way for subsequent generations of smartwatches, each offering new features and refinements. The Pebble's legacy endured, influencing subsequent generations of smartwatches with its practical design and long battery life. Despite its monochrome display, the Pebble could show images, though in black and white. Unveiled in 2014, the Apple Watch marked a significant shift in the smartwatch landscape. Unlike many of its predecessors, the Apple Watch was not a standalone device, but rather an accessory designed to work seamlessly with iPhones. Its primary function was to extend the iPhone's capabilities, providing users with a smaller screen for tasks like checking messages or controlling music playback. The watch also had basic fitness tracking capabilities such as step counting and sleep monitoring. But it wasn't just about functionality. The Pebble had an impressive battery life of up to 14 days on a single charge, far exceeding the typical 1 or 2 days offered by many of its competitors. Starting off, our story takes us back to 2012, where a little Kickstarter project was born. Pebble Technology was a team led by former MIT Media Lab researcher. This choice was deliberate, aiming for legibility in bright sunlight while conserving battery life. The watch was compatible with both Android and iOS devices and featured a powerful ARM Cortex M3 processor clocked at 72 MHz, alongside 512 kilobytes of RAM and 4 megabytes of storage. Connectivity was established through a Bluetooth connection. Their goal was simple: create a smartwatch that was useful without being intrusive. On July 26, 2012, they launched their campaign seeking $100,000. What they got was an astonishing $1.2 million from over 82,000 backers, making it one of the most successful crowdfunding campaigns of its time. The Pebble Time smartwatch used an e-ink display, a stark contrast to the vibrant LCD screens we're accustomed to today. The Pebble's user interface consisted of a series of circular app icons arranged around the edge of the screen, allowing for easy navigation using a tiny dial. With the Pebble successfully funded, the company continued to innovate, introducing new features and watch faces. Fast forward a few years and we see the rise of another trailblazer, the Apple Watch. The early Apple Watches featured a round design with curved edges reminiscent of the iPod Nano. wearable technology has come a long way from its early days as a simple timekeeping device. The Samsung Galaxy Watch 6 Classic is a cutting-edge smartwatch that pushes the boundaries of wearable technology. The Garmin Venue 2 Plus is a top-of-the-line smartwatch that caters to fitness enthusiasts. The Fitbit Charge 6 is a highly anticipated fitness tracker that offers a host of health monitoring features. The O-Ring is a revolutionary new wearable that sets itself apart from traditional. The Huawei Watch 3 Pro is a rugged and durable smartwatch designed for outdoor enthusiasts. As we look ahead to the future of wearables, we can expect even more innovative and advanced devices that push the boundaries of what's possible. Now, where do you see the future of smartwatches heading? Will they continue to evolve into more powerful, AI-driven devices? Time is what prevents everything from happening at once. This is Crash Course Philosophy, and today we're going to talk about time. Last time we talked about space, and this episode was actually meant to air last week. But like a lot of things that have to do with time, it just didn't quite work out. One thing I did not realize until making this episode is how much time itself shows up in philosophy. And if you follow any of them closely, you'll notice that their rhythms are out of sync with the Gregorian calendar used by most of the rest of the world. But other than that, what's so interesting about time is that no matter how much of it we have, it always seems like we don't have enough, and we often feel like we're running out. Everything is new and exciting, and there's no telling what might happen next. It's like there's a whole universe packed into every moment. And when we think of time as flying, it can help us get things done. Other times, though, it can be helpful to slow down and savor the present moment. Like on the one hand, we know that time is a dimension and that space and time intertwined in a four-dimensional continuum. On the other hand, we experience time as a relentless arrow that points forward from birth to death. But if space and time are intertwined, then why does time only seem to move in one direction? Well, physicists have come up with a few theories. One idea is that the direction of time is set at the Big Bang and has to do with entropy, which is a scientific way of describing disorder. Another idea is that the direction of time depends on the number of particles in the universe. In a smaller universe, particles would collide more frequently, increasing entropy and speeding up the apparent flow of time. But in a larger universe, particles would collide less frequently, slowing down the apparent flow of time. And finally, there's the idea that time is relative and that the direction of time depends on the frame of reference. According to Einstein's theory of special relativity, time moves slower for objects that are moving relative to each other. So depending on your speed, you might experience time differently than someone else. When we do that, it is like we retuning our internal clocks to a different frequency and creating our own rhythm in time. And neither is more valid than the other. It all comes down to what we find most useful or meaningful in our particular situation. The key is to be aware of our assumptions about time and to recognize that they read just that, assumptions. Once we do that, we can start to see how our experience of time is shaped by our culture, our psychology, and our physical environment. And that can help us appreciate the beauty and complexity of the world around us. This is why it can be helpful to practice mindfulness, which involves paying attention to the present moment without judgment. If you want to help keep this channel free for everyone forever, you can join our community on a crowdfunding platform. By focusing on the here and now, we can slow down the relentless march of time and appreciate the richness of our experiences. But as we grow older, we start to take our experiences for granted. And time seems to fly by faster and faster. We tell stories and myths about time to make sense of it and give it meaning. In many cultures, the hero's journey mirrors the cycles of the seasons or the phases of the moon, and we mark the passage of time with holidays and festivals. Many religions have stories about the beginning and end of time, too. Like in Christianity, the story of creation tells how God created the world in 6 days and rested on the 7th day. And in some versions of Islamic eschatology, the world will end during a period of time known as the Great Tribulation. Buddhism teaches that time is an illusion, but it still acknowledges the reality of our experience of time and encourages us to use it wisely. In Hindu mythology, time is personified as the god Yama, who sits at the end of a 12-year cycle and blows his conch shell to signal the beginning of a new age. That's because our brains are wired to adapt to novelty. When something is new and exciting, our brains release a surge of dopamine. But over time, that dopamine response diminishes, and it takes more and more novelty to produce the same effect. In other words, the more experiences we have, the more they blur together, and the faster time seems to go. There's only a finite amount of time left to do the things we want to do, see the people we want to see, or even stay alive, and that can motivate us to change. Like when we realize we have to change our habits to stay healthy, or when we're faced with an urgent deadline at work. But sometimes we wish we could slow time down, especially when it feels like it's slipping through our fingers. When we were kids, time went really slowly, partly because school holidays seemed to last forever, and partly because adults seemed to move at a pace that was completely out of sync with ours. And while we might not be able to recapture the feeling of those long, lazy days of summer vacation, reflecting on that time and trying to relive it in our memories can be a way of reconnecting with ourselves and appreciating the passage of time. For instance, in Judaism, the day begins and ends at sunset, whereas in many other cultures, the day begins and ends at midnight, and Muslims count their days from the sighting of a new moon rather than from the vernal equinox. And of course, there are other calendars and ways of counting time all over the world. All these different ways of measuring time show how the way we structure our lives is shaped by both physical constraints and human choices. From the ancient Greeks to the present day, philosophers have been waxing poetic about the nature of time. And not just because they like the way it rhymes with Jim, although that probably is a big part of it. As children, we might have literally thought that time flew or dragged. But now we know better. We know that our experiences can change how fast or slow time seems to pass. If we're having fun, time flies. If we're bored, it drags. This is called psychological time, which measures the duration of events based on how intensely we experience them, and it depends on a lot of things like our mood, or how engaged we are with what's going on around us. When we think of time as flying or dragging, we're talking about psychological time, not physical time. But thinking of time in these different ways is important because it helps us navigate the world around us. The study of time is called chronosophy, and many think we need one to get through the other. But since we're already doing it, let's see if we can't learn something about each from the other. Let's start with some basics. We generally think of time as passing in one direction, moving forward from past to future, and we can use our psychological clocks, which are accurate enough for most purposes, to tell us when things are happening. But there's a lot more to time than just that. Philosophers distinguish between chronological time, which measures the duration of events in relation to other events, like the amount of time between the Big Bang and now, or between breakfast and lunch, and biological time, which is the time within living things that regulates growth, metabolism, reproduction, and behavior, like the circadian rhythm that tells us roughly when it's time to sleep. Even that raises questions, like what would happen if two biological clocks got out of sync? Would you still be you? Or what if all biological clocks stopped? What would that even look like? This kind of philosophical investigation helps us understand the concepts we take for granted. And since we can't stop time to see what it looks like, We have to use our imaginations and reason to try to figure it out. There are also different ways of measuring time. For example, there's the time measured by our psychological clocks, which are based on our perception of the regular recurrence of certain events, like the rotation of the Earth on its axis, which we measure as a day, or the time it takes for the Earth to orbit the Sun, which we measure as a year. Then there's physical time, which is measured by changes in the physical world, like the amount of radioactive isotopes in a given sample, which scientists use to date fossils, or the distance between celestial bodies, which allows astronomers to calculate how far away those bodies are. These different measurements don't always line up, like the psychological measurement of a year not always match up to the physical measurement of the time it takes the Earth to orbit the Sun, depending on how elliptical the orbit is or how fast the Earth is moving, and that difference can add up over time. So sometimes we have to make adjustments. Like in 2009, scientists added an extra second to the day to make up for the accumulated difference. But there are also cultural rhythms of time. Like every major religion has its own calendar and measurement of time based on its own stories and rituals. Socrates once said, "Time you enjoy wasting was not wasted." Think about all the metaphors we use to describe how time passes, like time flies or time drags. For example, when we're little kids, time seems to pass very slowly because we're experiencing the world for the first time. Of course, this isn't always a bad thing. Sometimes we need to move quickly to meet deadlines or make plans. We humans have also built all sorts of external mechanisms to help us keep track of time. From sundials and water clocks to atomic clocks and GPS systems, one of the biggest challenges in understanding time is reconciling our experience of it with our scientific understanding of it. So again, this all goes to show that the way we understand time depends on what we choose to focus on, whether that's our lived experience or our scientific knowledge.